Okay, I'm going to write the formulas for the Fourier series representation and the coefficient formula. This is the representation. I'm repeating these formulas again and again so that you may just remember them when necessary. And I recommend that you do the same. K from minus infinity to infinity, ak e to the minus jk, it's not minus, excuse me, it's plus jk omega 0 t. This is a combination of harmonics, which is the Fourier series representation. And in this representation, you need to know the Fourier series coefficients, and the way to extract the Fourier series coefficients is through the formula that we have just discovered, 1 over t integral over one period. Let me write it like this so that it doesn't necessarily mean from 0 to capital T. It just depends on how you choose it. X t e to the minus j k omega 0 t dt. So these two formulas are like the second formula at the bottom is the Fourier transform of x of t. We are transforming x of t to ak. And the top one is the inverse Fourier transform sort of thing. It is transforming ak back to x of t. Using these formulas, we will solve questions, of course. And there are a lot of questions at the back side of the book by Oppenheim. Many of those elementary questions have answers at the back side as well. So try to solve them and check whether you are solving them correctly or not. For the time being, I'm going to solve only one example question, which is a very typical one. For the solution of the others, before solving more elaborate questions, we will see a set of properties. Because in problem solving, using these two formulas only is very difficult. Starting from these formulas, as you see, especially the second one, requires integration. And from calculus, we all know that integration by itself is a headache if the x of t waveform is too complicated. So we have to use some properties, shortcuts, to be able to solve questions. But this is not a question like that. This will be solved by normal integration with the top formula over there. And the question is as follows. X of t is given as a rectangular pulse, which is 1 for t absolute value less than capital T1 and 0 if it is greater than capital T1 and less than half the period capital T over 2. You may find it a bit complicated for this representation, but capital T1 is in the center. The duration from minus capital T1 to plus capital T1, it is 1. And the overall period is capital T, which is larger than twice capital T1, of course, somewhere here. Let me give you a graphical example of how it may look like. This x of t on the time axis is like this. Suppose that capital T is here, then I will have a pulse like this from minus capital T1 to plus capital T1, and since this is a periodic signal, you must extend it with a capital of capital T, with a period of capital T, like this. So to the right and to the left, it's extending, and the peak is 1. So this is our periodic waveform. And what are the Fourier series coefficients of these things? Is the question. And we are going to use this top formula. Let's write it. AK is equal to 1 over capital T. We have to keep it as capital T because we don't know what it is. It's just parametric. Now I can see that an integral from 0 to capital T here, in this duration, is not very appropriate, because there we need two portions, one at the position that I indicate with my mouse here, and the other one around here. That's not very convenient, right? Why don't we just integrate from capital T over 2 minus capital T over 2 to capital T over 2. This range is more appropriate, because in the center of that range everything happens. So I'm going to do it that way. From minus capital T over 2 to capital T over 2, x of t e to the minus j k omega 0 t dt. Now, of course, we need to find the Fourier series coefficients one by one, or you must find a different formula for every k, or parameterize in terms of k. Now, let's start from the simple one. For example, A0. By the way, this A0 is the DC coefficient. It's the harmonic with a zero frequency that would correspond to the DC component of this waveform. Do you think that waveform has a DC component? I think so, because it's always positive. So the overall DC value is something positive. If you have a symmetric positive and negative cycle oscillation, then the DC would probably be 0, right? A0 would immediately, you can say, to be equal to 0. But this one is not 0. It's 1 over t. Now, from minus capital T over 2 to plus capital T over 2, within that range, only the central portion is non-zero. The others are 0. Only the central portion is non-zero. Therefore, the integration limits could be from minus T1 to T1. That would correspond to the non-zero central portion. And over there, what is x of t? Within this range, from minus T, yeah, it is equal to 1 times, what is e to the jk omega 0 t when k is equal to 0? It is e to the 0. And that is also 1. I'm finding a0 only, as you see. So this integral is twice of t1 over capital T. So this is a0, the DC component. Are we happy with it? This is the portion of the question that you have to solve, the DC component. What about the others? Usually the others are parameterized. Again, from minus T1 to T1 is reasonable, because otherwise it's all zeros. 1 times e to the minus j k omega 0. What is omega 0? Well, let's keep it as omega 0. It is 2 pi over capital T, if you wish. You can also write it like that. But that's not very important. We somehow need to integrate this. Exponent integration is one of the easier integrals. So we can proceed. 1 over capital T minus 1 over jk omega 0 times e to the minus jk omega 0 t from t1 to minus t1. So 1 over the exponent is inserted here. This minus is due to the fact that there is a minus in the exponent, e to the minus something. So its integration would be 1 over minus jk omega 0, in other words. So this is the thing that we need to evaluate. Let's try to be more precise. This is equal to, there is a 1 over j term coming here, and in one term we have a positive exponent. In one term we have a negative, in the other term we have a positive exponent. So if the exponents are 1 positive, 1 negative, and if there is a 1 over j, and the difference is with a negative sign, that would there's a possibility that it will be converted using the Euler's transform into a sine. This will hopefully be transformed into a sine. So this is what I'm going to do. 2 over capital T times 1 over k omega 0. Why did I put 2? Because in the denominators of the other terms I'll put a 2. And I will also put these j in the denominators of the others. When I put them, you will understand what I mean. E to the, no, it's not minus. The first one is positive. J k omega 0 t1 minus e to the minus j k omega 0 t1 divided by 2j. You see that this j comes from here, and by putting a 2 in the numerator, I was able to put a 2 in the denominator. Why did I do that? Because this huge right-hand side term is now a sine. It's the Euler's expansion of a sine. And when we expand it, that would correspond to 2 times sine k omega 0 t1 divided by k omega 0 capital T. Perhaps I should have eliminated or cancelled some of the terms and simplified them beforehand, but now we can do that. Do you remember what omega 0 is? Omega 0 is 2 pi over capital T. So 2 pi over capital T times capital T is 2 pi. So we have a 2 pi here, and we have a 2 here already. So those 2's will also be cancelled, and we will have sine k omega 0 t1 divided by k pi. Quite simple, compact expression formula. 10 points. When you write it like this, it means you found the Fourier series coefficients, AKs precisely, and they happen to be this. Now, if this T1, which is a general duty cycle, the high duration of this pulse, is also related with the overall period. In some cases, that is the case, and let's see an example for that. Example is the period is 4 times T1, so that would make a half duty cycle. In half of the time it is 1, in half of the time it is 0, and then 1, and then again is 0. This is a very common case for a digital pulse. If that is the case, then AK will be equal to sine. Now look at the formula. K times omega 0 times T1. And T1 is capital T over 4. So K times omega 0 capital T over 4. And omega 0 is 2 pi over capital T. Those capital T's are cancelled. We have K pi over 2. That's what I'm going to write here. Excuse me. K pi over 2 divided by K pi. These are the Fourier series coefficients of half duty cycle digital rectangular pulse, which is the thing that I was mentioning last hour. That is a very common thing that we find in power systems, basically. Why? And why is it significant? I told you that there are only odd harmonics. There's only A1, A3, A5. How about A2 and others? What happens to A2? What happens to A4? What is A2? Just substitute 2. Sine pi over 2 pi. What is sine pi? 0. When k is equal to 4, it is sine 2 pi. Sine 2 pi is even more clearly a 0. Sine 6 pi. All those even multiples of pi will give you all multiples of pi. Sine of integer times pi will be equal to 0. And we will have a1, of course. a1 is equal to some value. It is sine pi over 2. What is sine pi over 2, by the way? 1. Therefore, a1 is equal to 1 over 1 times pi, which is 1 over pi. So the Fourier series coefficient of the first harmonic is 1 over pi. What is a3? What is sine 3 pi over 2? Say it? Minus 1, exactly. Then a3 is equal to minus 1 over 3 pi. 3 pi. Let's write a few more. a5 is equal to sine 5 pi over 2. Then that is again 1. So it is alternating in sign. 5 pi. a7 is minus 1 over 7 pi. This is a very commonly encountered situation in power systems. The harmonics are only odd harmonics and their signs are alternating. One positive, one negative, one positive, one negative. And even harmonics are all zeros. A2, A8, A100, etc. They are all equal to 0. So this is an example. And this example is so famous that you may want to even memorize this formula for a rectangular periodic pulse train. Because this, if you remember this, we will modify this, shift it to the right, shift it to the left, multiply it with something, invert it in some cases, etc. And I will ask you another question. And all the questions you will think of, what is it? What is that periodic signal in terms of this rectangular pulse at the top? Can I represent my periodic signal in terms of this? And if you can, then you will use this answer here and use the properties, some formulas, to translate or transform this answer to our new answer. This is a very important Fourier series example in that aspect. It's an easy one, but it's important. Yeah.
Bu AK'nin formülündeki kaydırmaları yapmak için geçen dersin başında impulse response 3'te kaydırmıştık ya. 3'te kaydırmıştık mesela.
I get it.
Geçen derste impulse response 3'te kaydırdık. Pardon, system delay sistem olarak.
But it was a system. There was a system there. Here we don't have any. No. We have no system here. We are just finding the Fourier series coefficients of a given signal, nothing else. We are not passing this signal through any system. But that's a very good idea, by the way. What would happen if you pass this signal through a system of 1 hour before? The delay, 3 seconds delay system. How does it behave? That would be a good exercise to find what is the output if I input this signal, the top signal, into that system. But unfortunately in this question there is no system, there is no delay, nothing. This is just plain signal and we are finding the Fourier series coefficients of the signal. In order to proceed with the questions, the first thing is to find the Fourier series coefficients. You have to find them. In many cases, the exam questions will be like, find the Fourier series coefficients of this signal that I draw. And you have to give me an answer. And your answer should be like this. AK is equal to this, you have to say. Except for K is equal to 0 in many cases. By the way, why did we find A0 separately at the top? Why didn't I just give you this answer and say that AK is that, including K is equal to 0? Do you see the problem there? Yeah. There's a denominator with K. So it's a 0 over 0 division. Sine 0 is a 0, divided by 0. You have to use the famous Hospital's rule to find A0 as a limit from this AK, and that would be exactly the same as this answer, by the way. Please verify. Please verify that. Apply the Hospital's rule to this sine k omega 0 t1 over k pi. For k is equal to 0, what is the limit of that? And you will have to find it to be equal to 2t1 over capital T. But of course, that's a little bit more difficult. That's why usually A0 is considered separately. K may be in the denominator, which is a problem. So these are the Fourier series coefficients only. We're not talking about any systems. Okay? Now, in the first minutes of this Fourier series or Fourier-related chapter, I mentioned about the story of Fourier, if you remember, and said that when he discovered this thing of Fourier series representation, people didn't believe. Because as you see, look at the periodic shape. It's consisting of rectangular pulses, very sharp, very discontinuous at those points. And Fourier claims that even this one is a combination of smooth sinusoids with changing frequencies. And that's amazing. And what is even more amazing is that, just take a look at this AK expression, sine k omega 0 t1 divided by k pi. This sine, the numerator, is bounded between -1 and 1. It's a sinusoid. So its magnitude is between -1 and 1. However, the denominator is k pi, and as k increases, the denominator also increases, which means that as k goes to infinity, the Fourier series coefficient magnitude is decreasing. Look at that. 1 over pi, and then -1 over 3 pi, and then 1 over 5 pi, and then -1 over 7 pi. It is decreasing in magnitude. The value is shrinking. And at A infinity, we will get a zero shrinkage. That's usually the case. We have infinitely many harmonics, that's okay, but the harmonics of the higher frequencies will decrease in energy. So it's a convergent case situation. And even this discontinuous periodic shape has some finite and convergent series summation of sinusoids. Therefore, people didn't believe. You remember that? I was mentioning about the story of Fourier. But later on, of course, they believed and they understood the philosophy, the mathematics behind it. Later on, his student, his doctorate student, PhD student, which is Dirichlet, student of Fourier, also discovered the cases or the restrictions where you can always find the Fourier series, because although when I said if you have a periodic signal there is always a Fourier series representation, I was lying to you. It's not always the case. It must obey the so-called Dirichlet. What is this? Yeah, Dirichlet conditions. It must obey the periodic signal. But these conditions are very nice conditions. Almost all reasonable periodic signals already obey these Dirichlet conditions. First of all, within a period, the absolute integral must be finite. So it mustn't be an infinite blowing periodic signal. That's reasonable, right? Normal signals are always like this. Within a period, they are bounded. If they are not bounded with an infinite integral, then you cannot find or you cannot talk about the Fourier series coefficients. This is condition number one. So what can we give as an example to this? The arctangent. Or Or is it the tangent? The tangent was this curve, right? Plus infinity here, minus infinity here. So if you're talking about a periodic signal, which is the tangent signal, then Fourier series coefficients cannot be found, for instance. The second condition, in one period, within one period, in other words, the number of oscillations must be finite. So within one period, there mustn't be an infinitely oscillating situation. Let me give you a counter example. This is so normal that it's even difficult to imagine a periodic signal which is showing infinite oscillations within one period. But one signal is this, for example, sine. So x of t is sine 2 pi over t between 0 and 1. And then it repeats itself. So I'm defining the signal within a period, and then I'm repeating it, so I make it periodic. But within one period, look at what's happening as t goes to 0. As t approaches to 0, 2 pi over t is growing like a crazy. And therefore, the sine of it will make infinitely many oscillations. Just try to visualize what sort of a signal is this, around 0. It is, it's a sinusoid, so it is between -1 and 1. But it is something like this, infinitely many oscillations, and then the oscillations become wider as t increases. Such signal, and then you define it within one period, for example, and then you repeat it, so you make it periodic. But the number of oscillations is infinity. And the name of such a signal is called the chirp signal. The chirp is the voice of a bird. Since the voice of a bird is changing the frequency from high to low or from low to high, such variations in frequencies are notated as a chirp signal. That's the English name. Sort of thing. What is the third condition? The third condition is within a period, the number of discontinuities must be finite. This is even more difficult to imagine. What sort of a discontinuous signal can you have so that the number of discontinuities is infinity within one period? Then you repeat it, of course. The rectangular pulse is not an example to that because it is discontinuous only at 2 points. So the number of discontinuous points within a period is 2, not infinity. Therefore, we have the Fourier series. If it is infinity, then we cannot talk about the Fourier series. Let me try to think of a counterexample. The counterexamples are usually fabricated, as you see, and normal signals always have Fourier series coefficients. Let's assume that this is the period capital T, and my signal is like this. From 0 to capital T over 2, towards the half of it, the signal value is 1. And then the value is halved. I have the half value. And towards the remaining, half of the remaining, I keep it to be equal to that value. And then make it half again. And then until the half of the remaining distance, it is half. And then I will make it half again. And then it will remain half until the half of the remaining. And then make it half again. And then leave it like that. And then half again, and then half again. There are lots of small halvings going on here, around here. And the number of half operations is infinity. because you can never reach to the end. You always go half the remaining, so you can never reach there. And the number of those discontinuities is therefore infinity. So this is a counterexample. And then of course you repeat the same signal to the right, to the left, and make it periodic. In the nature you can never come up with such things. They don't exist. They are just hypothetical. But these are the Dirichlet conditions that your signal must obey, which is very easy to obey. Now, in the rest few minutes, 10 minutes or something, I will start the Fourier series properties. These properties are the keys to solving questions. Okay? The formula of the Fourier series coefficient formula, the integral, and the Fourier series expression formula, the two formulas at the top, they don't really help us solving questions. They are the final or last resort. I mean, if you cannot think of any property, if you cannot think of anything, the last thing that you can think of is, okay, I'm finished. Let me apply the integral formula and solve it. Let's try to solve it. It is highly not recommended. Okay, don't do that. The key to solving questions are utilizations of these properties. What are they? We will have, of course, a relation like this. And I will indicate the Fourier series on the top of the double-sided arrow here. Every x of t is associated with the corresponding Fourier series coefficients, with the formula. Now, the situation, and let's write another Fourier series relation with the same frequencies, or with the same fundamental frequencies at least. The first relation is, the first property is the linearity. It's like the properties of the systems. By linearity, what I mean is this. If you construct a new signal, z of t, as a times x of t plus b times y of t, then the Fourier series coefficients of this z, the new z, let's call them ck's, are equal to a times ak plus b times bk. So you can combine the Fourier series coefficients. But remember that, you have to always remember that these k indices for both x of t and y of t must correspond to the same frequency. So if the fundamental frequency of x and y are different somehow, then you have to find a common fundamental frequency first and notate or rename ak's, the indexes of k's, integer k's, corresponding to the common frequency only. This is valid as long as omega zeros are the same. Alright? So this is the linearity property. Now, using the linearity property and this new property that I will say, which is time shifting, I can construct a lot of exam questions. Because you already know the Fourier series coefficients of the rectangular pulse. It was there. Okay? I can combine one rectangular pulse and the same periodic, different, slightly shifted, perhaps negated version of a different periodic pulse train. And then I can ask you what are the Fourier series coefficients of this new thing. Let me give you an example question. I will continue with this time shifting after the example. I'm not going to solve this example, by the way, but it's a nice way of looking at things. Suppose you have a periodic signal given like this, where capital T is something, it's given to you. This value is, let's say, 2, and this value is 1, and let's give a specific value to this. Let's say this is 8, this is -1, and this is 1. What are the Fourier series coefficients? If I were you, I mean, you can attack this problem in two separate ways. You can either say that one of the signals is this, the red signal, and the other signal is the blue signal, and I will find the Fourier series coefficients of the red pulse train and the blue pulse train. You can do that, you can find them. It's just using the time shifting property that we haven't mentioned yet, but we are going to see it right now. When you shift the signal, what happens to the Fourier series coefficients? It's a small perturbation. So you will perturb them like this, and then you have to combine the Fourier series coefficients by multiplying the Fourier series coefficients of the first one with 2 and adding them to the Fourier series coefficients of the blue pulse train. There are two individual pulse trains going on here, the red pulse train and blue pulse train. Find them isolated, separately, and then combine them. You can do that. You can use the property to solve the question like this. So it's a very impractical way of doing this problem if you solve this question like this. If you take an integral from here to here, and over there, within this region, you have a different integral, and within this region, you have another integral. Probably that will be a very complicated and difficult way of finding the integrals. So don't do it that way. Instead, find the Fourier series coefficients of the red and the blue pulses. But that's only one way of attacking the problem. You can do it in another way. You can say that these shapes are a combination of these green pulses and another black pulse like this. When you add up the small black ones here, 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 and there, with the green pulses like this, when you add them up, you will also get the same shape. So you can solve the question like that too. Find the Fourier series coefficients of the green and the black, and then combine them using the linearity property. But how are you going to find the Fourier series coefficients of these red, blue, and green and black portions? For that, you need to use the time shifting property. So if x of t has Fourier series coefficients of a case, and we will say y of t is equal to x of t minus t0, a shifted version of the signal, and y of t has Fourier series coefficients of bk's. What are bk's? What are the Fourier series coefficients of the shifted versions? We can derive it, it's not very difficult, by the formula of integral 1 over t within a period of capital T, y of t, which is x of t minus t0, e to the minus j k omega 0 t dt. This is the formula of the Fourier series coefficients of y of t. Okay? Because here I have y of t. Now let's change t prime by t minus t0. So bk will be equal to 1 over capital T within the same period. The period integrals will be shifted by t0, but as you remember, it doesn't matter. It doesn't matter where you start and end. It just has to have a duration of capital T. And inside it, I will have x of t prime and e to the j k omega 0 t prime plus t0 dt prime. I can write it like this. Now e to the j k omega 0 t0 is independent from the integral parameter t prime, so it can be taken out of the integration. E to the, of course there must be a minus sign here, e to the minus j k omega 0 t0 over capital T integral within T x of t prime e to the minus j k omega 0 t prime dt prime. So this is the new formula, and in this new formula we can, with close inspection, see that the right hand side of the whole term corresponds to ak. So that will give you a relation between bk, the shifted versions for series coefficient, and ak, the original. And oops, and what is it? It's bk is equal to e to the minus jk omega 0 t0 over capital T. Oops, sorry, there is no capital T or a division because that over capital T is already in this formula. Alright, so bk is e to the minus jk omega 0 t0 times ak. This is the shifting property. If the fundamental period is, if the fundamental frequency is omega 0, then every bk of the shifted signal is the original Fourier series coefficient multiplied by a complex exponential like this. This complex exponential is not a function of time, of course. There is no time information here. It's just in terms of k. It's just an index in terms of k. That is usually the case that you will have to remember. If you shift your signal, its Fourier transform will be multiplied by a complex exponential. We will see that again and again. This is the first example that we will encounter, we have encountered. We will continue with a lot of more Fourier series properties, but let's stop at this point. Tomorrow we will finish them and start seeing examples about that.